All right, so mic check, 1, 2, 3, sounding good. I usually like to, even in this room, I like to go without a mic and I just yell. So it's something I'm going to have to get used to. But yeah, so I guess I won't repeat any of my own biographical information. I do synthetic organic chemistry research looking at medicinal chemistry for cystic fibrosis, which is a genetic disease. But I'm actually not going to talk about my own research today. What I'm going to tell you is more of a historical perspective of kind of the field of pharmaceutical chemistry. What I'm going to try and tell you, actually, is this interesting connection that if the mosquito were not so abundant, or a certain species of sea snail so rare, the pharmaceutical industry as we know it today might not exist. And so it's a story of pharmaceutical chemistry, but really more than that. Pharmaceutical chemistry is a very broad term. There are lots of aspects of pharmaceutical chemistry that I'm not going to talk about today. I'm going to talk primarily about organic synthesis, synthetic organic chemistry, which is really what I do, and it's the history of it. So if we're going to talk about organic synthesis, I'd better define the terms. So we'll start with organic chemistry. And I like to start my definition of organic chemistry with what it's not, because this word organic gets used a lot in modern times. You often see it used to describe farming practices or produce designations, and sure, there's a such thing as organic produce. But whether a corn plant is lovingly hand fertilized with the manure of a free-range chicken, or whether it's been sprayed with the latest pesticide from Monsanto, that corn is made of organic molecules. So it's not a statement about farming. It's not a statement about whether something is natural versus man-made. It's not a statement about whether something is safe versus toxic. And here's an example of that. The structure on the left is Kalydeco, a drug used for the treatment of cystic fibrosis. And it is a completely man-made substance invented by people. It is safe to consume for cystic fibrosis patients, and in fact, it improves the lives of several cystic fibrosis patients. On the other hand, on the other side, we have tetrodotoxin, another organic molecule, isolated, a natural substance isolated from the pufferfish, and it is incredibly toxic. A 25 milligram dose of this material is enough to kill the average person. Both of these are organic molecules, so it's nothing to do with safety or natural or man-made. So what is it to do with? Very simply, organic chemistry is the chemistry of carbon. If a molecule has carbon in it, it's most likely organic. Usually in modern definitions, we have this stipulation that it has either a carbon-carbon or carbon-hydrogen bond in it. But otherwise, if it has carbon, it's an organic molecule. So here's a couple of examples of molecules that are inorganic with carbon. Sodium bicarbonate, baking soda, or silver isocyanate that we'll see in a second. Here, the carbon is only bonded to oxygen or oxygen and nitrogen, and those are generally considered to be inorganic carbon. But otherwise, molecules that have carbon in them, especially with CC or CH bonds like ibuprofen, the pain reliever that you find in Motrin or Advil, are organic. Now at this point I'm going to do a brief aside about the way that I draw organic molecules in this talk. If we look at this structure of ibuprofen, we'll notice a couple of things. One is that it's very busy. You look at it and there's a lot going on, a lot of atoms there. But one of the things that we can use to simplify this structure is knowing that every carbon atom forms 4 bonds. If we look at every carbon here, each of them forms 4 bonds. Since all chemists know this, and this is always true, carbon always forms 4 bonds, what we do as a shorthand to draw organic molecules is we get rid of all the atomic symbol C for carbon, we get rid of all the hydrogen atoms attached to carbon because we know they're there. So in this structure, this carbon atom, which we show 3 bonds, 1 there and 2 there, we know that it forms 4 bonds, so it's implied that there's a carbon here and a hydrogen attached, just like in this structure. So from here on, I'm going to be using these skeletal structures to draw organic molecules, but it's important to recognize what they mean. Okay, so that's organic chemistry. What's the synthesis part? Well, synthesis basically, sometimes it's referred to as total synthesis. It's basically where we take substances that we can get our hands on, readily available substances, we do reactions to them to make them more complicated, and then we take those substances, which are now available because we've made them, and we do more reactions and more until we build up something that is interesting and useful. Sometimes it's a natural product, a drug, etc. So just in a kind of a schematic form, if A and B are readily available, and I do a reaction to make C, which is not, well, now it is. I've got some C on the shelf. If D and E are available and I make F, and then maybe I react C plus F to make perhaps a drug. This is what organic synthesis is about. So the first organic synthesis takes us back quite some time to well, actually, I guess I'll first say is urea was first isolated from urine. So that's where it gets its name. Isolated from pee by a French chemist in the late 1700s. And so because it's isolated from living things, he called this organic. Now, by my definition, the definition I just gave you, it does not have a CC or CH bond. There's a carbon right here, but it's only bound to oxygens and nitrogens. Maybe not organic by today's definition, but certainly back then, this was an organic molecule. In 1828, a young chemistry student by the name of Friedrich Wöhler found that he could react silver isocyanate, an inorganic carbon source, and ammonium chloride, heat those up, and lo and behold, he found out of this reaction, he got silver chloride precipitate and urea. And this was a eureka moment. So he's a student. He proclaims to his mentor, I can make urea without the use of kidneys, be they human or dog. This maybe doesn't seem like that big of a deal to us, but back then, they thought that organic substances could only come from living things. This was a theory called vitalism. And that these organic substances had a vital force, something special that was given to them by coming from living sources. And this basically proved that there's no such thing as the vital force, and that it is possible to synthesize organic molecules from readily available substances. So this essentially spawned, now that you've broken this barrier, people are starting to want to make natural substances from whatever they can. So where does the mosquito fit into all of this? Well, mosquitoes cause malaria. Not that big of a problem in North America in 2014. It is still a big problem around the world, in certain parts of the world. And certainly back in the mid-1800s, malaria was a problem. It causes very bad fevers, and in some cases, other symptoms that basically lead to death. This is a bad disease. So it was known, even from the mid-1500s, that if you chewed on the bark of Cinchona calicea, the fever tree, it would help to reduce your fever, and therefore this was a treatment for malaria in the mid-1850s. And they knew that you could, in fact, extract a substance from the cinchona bark called quinine, and that's the structure of quinine. And since there's no vital force, people thought we should try to make quinine in the lab so that we can distribute it widely and maybe cure malaria. This was the idea behind a professor at the Royal Chemistry of College in London by the name of August Wilhelm von Hofmann. He's a professor there. He wants to make quinine. So he gets a young student by the name of William Henry Perkin, and this is going to be his project. You're going to make quinine. And here was his hypothesis, Hofmann that is. He figured, well, let's heat together aniline and these two isomers of toluidine with some sulfuric acid and potassium dichromate, and that's going to make quinine. Now, I'm a synthetic organic chemist, and I can look at this and I can tell you that this is complete nonsense, right? In order for a reaction to make something else, the reactant often looks at least a little bit like the product. Reactions do subtle changes. So this does not have a hope of working. Does that mean Hofmann is an idiot? Well, not really. This is the 1850s, and there are a number of things that weren't known at this time. William Odling, only in 1855, proposed and cemented the idea of the tetravalency of carbon, this idea that carbon always forms 4 bonds. That was still up for debate up until the mid-1850s. And Van 't Hoff and Lebel, only 2 decades later, proposed the idea of the three-dimensionality of molecules. Carbon forms 4 bonds. Those 4 bonds point out in different directions. And if this is a carbon and this is a nitrogen and it points there, that's different from the same carbon bonded to the same nitrogen pointing there. Those are 2 different molecules. So, and that was a very important idea. Van Hoff won the first Nobel Prize in chemistry in 1901 for proposing that idea. And without these 2 ideas, there is no way Hoffman knew that this was the structure of quinine. So he's going into it blind. He doesn't know this is the structure of quinine. All he would have known from a process called combustion analysis is the molecular formula of quinine is this, C20H24, N2O2. So this is a process where you burn a sample of known mass, and then you measure and quantify the smoke of various kinds that comes off the material, and you can determine the molecular formula. This was something they could do in the 1850s. So they wouldn't have even necessarily known the structures of aniline and toluidines. They would have just known this. So now when we look at this, we see, well, oh, there's about 20 carbons here, and there's 20 in the product. There's enough hydrogens to get, maybe you burn some off and make water. Maybe you burn off a nitrogen and you get an oxygen from one of these reagents. And maybe when you do all this, you'll get that. Maybe not so ridiculous. So Perkin tries this reaction. And he gets black tar. Now, as a synthetic organic chemist, I can tell you, when you mix certain reagents and you get black tar, that's a bad thing. Quinine is a white powder. So you couldn't get further from white powder than black tar. Now, this doesn't mean you drop out of school and give up. What Perkin does is he thinks, well, maybe the white powder is hiding in the black tar. Maybe I can extract it with some methanol. So he treats this black tar with methanol, and he gets a deep purple solution. So it's still not quinine, but he's got this purple methanol solution. And he thinks to himself, well, I wonder if I could use this purple solution to dye fabric. Now, that connection that he made there is a rather important one. Prior to 1856, when Perkin tried this, dyes, all dyes on fabrics were isolated from natural sources. So we had substances like alizarin, a crimson red dye. Again, this structure wouldn't have been known in the 1850s, but they knew you could isolate alizarin from the root of the madder plant. Or cochineal dye, a red dye made by grinding up the bodies of the cochineal beetle. Or a purple dye made from a really disgusting process of fermentation of the feces of birds and lizards. But the most precious dye of all was called Tyrion Purple. Tyrion Purple is a secretion of this rare sea snail, Bolinus brandaris. And it had been known for over 2,000 years, since biblical times and before. This dye was so expensive it was worth its weight in silver. And so only royalty could afford this dye. And if you see old paintings of royals, they're always wearing purple robes. That was Tyrion Purple. So Perkin recognizes this purple solution he's accidentally made when he's trying to make quinine resembles a solution of Tyrion Purple. And he thinks, maybe now the poor people or just the common folk can wear purple too. So he patents this process, and he drops out of school. He opens a factory to manufacture this purple dye, which he calls mauve. And he essentially creates an industry for synthetic dyes almost overnight. People instantly realized, if he can do it, so can we. And so I'll tell you about some of the companies that popped up very soon after Perkin made this discovery. Oh, first, I'll just mention that the structures of Perkin's mauve didn't fully become understood until over 150 years later. Just very recently did we learn that it's a mixture of things, and we can see those aniline molecules in there and those toluidine molecules, and they come together in random kind of ways, but overall they make purple. And so this class of dyes came to be known as aniline dyes, and especially in Germany, a lot of chemistry was happening in Germany at the time, there were companies coming around. The first of those companies was 1865 Badische Aniline und Soda Fabrik. My apologies to any Germans in the audience, I probably butchered that. But basically it means aniline and soda factory. And aniline, of course, is for aniline dyes. And they made synthetic indigo, which is the blue dye that, if you're wearing jeans right now, is dyed with indigo. They developed a synthetic way to make alizarin, which was previously only available from the root of the madder plant. Interestingly, they filed the patent on that process one day before Perkins' company did. This company, Badische Aniline und Soda Fabrik, is still around today, but you might know it better as BASF. And BASF is one of the biggest chemical companies, in fact, one of the biggest companies in the world, with annual sales last year nearly 74 billion euros. That's just one of the companies, founded on the discovery of synthetic dyes. Another one, Höchste Dye Works AG, one of their first products was this fuchsine, a fuchsia dye. Now they have been around and been bought out by other companies, et cetera, over the years. That company is now called Sanofi. It is one of the biggest drug companies in the world. Sales last year of nearly 33 billion euros. One of their biggest drugs is Plavix, this coronary artery disease treatment. That most recent number I could find was $9 billion in sales in 2010. Again, started as a dye company. Last one I'll tell you about is SIBA. They made fuchsine as well, this fuchsia dye. They also extracted dyes from plants, and they extracted even quinine for anti-malarial. So there's like more connection. Again, mergers and acquisitions over the years. SIBA became SIBA Geigy. Eventually that got bought out by a company called Novartis, which also still exists today. Also a huge company. One of their biggest drugs is Gleevec, which is a cancer chemotherapy with sales nearly $5 billion. So again, all these companies launched on the discovery of synthetic dyes. So Perkin, famous for having invented aniline dyes, he also invented some perfumes and some other industrial processes. He eventually, in 1874, just got tired of competing with these big German companies. They were getting bigger and bigger and bigger. So he retired, very, very wealthy, at the ripe old age of 36. And still a very famous name today. There were some famous organic chemistry journals named after him. The site where he first did that experiment is a historical site in London. And so that's the story of William Perkin. Now, his boss, Hoffman, I don't want to leave you thinking that he had this dumb idea. So he went on to also become a pretty famous chemist. Not a rich man, but a famous chemist. He moved on to the University of Berlin, where he was the chair of chemistry until he died in 1892. And I'm not going to go into too much of the chemistry, but he invented several organic reactions that are important still today, and they're named after him. For instance, the Hoffman elimination and the Hoffman rearrangement. So he was an important guy too. So this synthetic dye industry is now booming. It's the late 1800s. People are doing research, trying to come up with new ways to make synthetic dyes. And one of these classes of dyes, we had the aniline dyes, was azo dyes. So this is a discovery where if you took aniline and treated it with sodium nitrite and hydrochloric acid, you get a molecule called a diazonium ion. So this is a diazonium, has an NN triple bond and a positive charge on one of those ends. And when that reacts with a second molecule of the aniline, and we won't worry too much about what these arrows mean, they form a bond and you get a molecule that has this NN double bond, and this is a yellow substance, and they called this aniline yellow. And this became now a new way to make synthetic dyes. And so this again launched a whole other class of azo dyes, and here's a bunch of them. And the only main point I want to point out is that they all are made by the same diazonium chemistry. They all have this NN double bond in the middle of them. And this is what leads to the next part of my story. So in the mid-1870s, a young postdoctoral student by the name of Hermann Emil Fischer is doing research in an academic lab, a lab of Adolf von Baeyer. And he's experimenting with diazonium chemistry, this chemistry used to make azo dyes. So he makes the diazonium salt, but then instead of reacting it with another aromatic ring to make a dye, he reacts it with sodium bisulfite, and he gets this substance called phenylhydrazine. So what's happened is he's reduced the NN triple bond into a single bond. These substances with NN single bonds had not been known prior to this. So he invented this. Now, that's all well and good. What are these useful for? He went on to continue studying these. And what he found is that when you react phenylhydrazine with an aldehyde or a ketone, so that's a molecule that has a carbon-oxygen double bond, that it condenses, so you lose a molecule of water, H2 and O, and you form a bond between this carbon and that nitrogen, a double bond. These molecules are called phenylhydrozones. Phenylhydrozones are solid crystalline materials, and in the late 1800s, the way to identify compounds, aside from combustion analysis, was by their melting points. So if you had a way to make something that was a solid, whose melting point you could measure, you had a way to indirectly identify substances. So if I have an authentic sample of a certain aldehyde, I can measure its melting point, and then if I have an unknown and it has the same melting point, maybe they're the same thing, but it could be a coincidence. If I take the authentic aldehyde and make its phenylhydrazone, and then I take my unknown aldehyde and make its phenylhydrazone, and they have the same melting point, then it becomes much more likely that these two are the same thing. This was cutting-edge stuff in the 1870s. So Fischer became a lecturer at Munich shortly thereafter, and then an associate professor at Munich, and then he became a full professor at the University of Erlangen in 1881. And this is where he went on to do some of his really groundbreaking work. Some of the first things he was interested in were the chemical synthesis of extracts from coffee, tea, and cocoa. So we have caffeine, theobromine. Again, from combustion analysis, all he would have known is their molecular formulas. But he proposed that these things were chemically related to a structure that he called purine that looked like this. And indeed, through organic synthesis, he made synthetic caffeine and theobromine and showed indeed that they have that same parent structure as purine. He was the first to synthesize these two and several other purines as well. So some of these you've heard of. Adenine and guanine are the nucleobases in your DNA, A and G. Xanthine and uric acid, all of these have that purine structure. So that's one of the things he did, kind of important at the time, but one of the most important things Fischer did was his work on sugars. Fischer wanted to prove the structures of certain sugars like glucose, mannose, and fructose. So at the beginning, what he would have known is their molecular formulas, and if you look at these, they're all identical. He would have also known that glucose and mannose are aldehydes, and fructose is a ketone. So these things are isomers of each other. They have the same formula, but they must have different structures. Obviously, with things like sugars, you could taste them. You would know they're different because they taste different. So he had invented phenylhydrazine, and these are carbonyl compounds. So he reacted them with phenylhydrazine and got phenylhydrozones, and those all also had different melting points as expected because they're different substances. But he was just basically trying to build up some body of knowledge about these things so that he could figure out their structures. So then he tried a reaction where he, instead of one equivalent of phenylhydrazine, he used an excess. So if I have 1 mole of glucose, I would react it with 3 moles or more of phenylhydrazine. And in this case, he got a precipitate called ososones, that he called them that. Now, for the moment, it doesn't matter what ososones are. What's interesting about this is the ososone from glucose or mannose or fructose were all identical. So whatever the ososone is, it's converted, it's come from 3 different things, but it's made the same thing. So the ososone reaction, again, we don't have to worry too much about the nitty-gritty here, is that first we're making a phenylhydrazone from the C double bond O, and then we're making another one from an adjacent alcohol. And we're getting 2 hydrozones on the same molecule. So recall just not too far earlier, Van Hoff and Lebel proposed this idea of stereochemistry. When a carbon has an oxygen here, it's different from having it here. And Fisher's hypothesis was that the differences between glucose and mannose and fructose, aside from the aldehyde versus ketone, was whether the OHs were on the left or the right. In other words, he proposed that glucose and mannose differed from each other by whether the OH here was on the right versus the left, and then fructose was the ketone, so these two carbons were switched around compared to those. Now, that doesn't say anything about the structures of these ones. We don't know if the OHs are on the left or the right, but what must be true is that for glucose, mannose, and fructose, these parts in red must be identical, because when you make the osozone, you get the identical product. This is what he's building on now. So he hasn't solved the problem, but he's got a good hypothesis. To solve the problem, he had to develop a method to synthesize sugars. So, and again, there's a lot of heavy chemistry here that I'm not going to go into, but the bottom line is he developed a method with a guy named Kiliani that would start with a sugar, and in this case it's a 1, 2, 3, 4, 5 carbon sugar. And through this process of several organic reaction steps, he would turn that one sugar into 2 separate 6 carbon sugars. So if we start with a 5, we get the 6. And the key thing is the differences between these two, the parts in red will be identical because they came from the starting material. But the OH at the topmost carbon, one of them will be to the right and one of them will be to the left. And he found that when he started this whole process with a sugar called arabinose, isolated from gum arabic from the acacia plant, that the product he gets from arabinose were, in fact, glucose and mannose. So we still haven't solved the structure of glucose and mannose. But what we have determined is that the left or right of these OHs in glucose and mannose must be identical to arabinose. So now if we want to solve the structure of glucose and mannose, we need to solve the structure of arabinose. If we want to solve the structure of arabinose, we have to start with a sugar that has 4 carbons. And if we want to know the structure of that one, we have to start with a sugar that has 3 carbons. And so this is what Fisher did. He started with the 3 carbon sugar. He made both of the 4 carbon sugars. From each of those, he made all 4 of the 5 carbon sugars. And from each of those, he made all 8 of the 6 carbon sugars. And in so doing, he proved the structure of glucose and mannose and several other sugars that were known at the time. He predicted the existence of some of these sugars that were not yet known at the time. But they were discovered later, so they proved him right. And he showed that the differences between all of these sugars was just the stereochemistry, whether the OH was to the left or the right. So Hermann Emil Fischer was kind of like the grandfather of synthetic organic chemistry. Perkins started it all, but by accident. Fischer really looked at this problem like science. And he did a lot of important contributions. He invented phenylhydrazine in the hydrozones and ososones. He synthesized the purines. He showed ways to draw sugars. He made a bunch of sugars. He invented a whole bunch of reactions that I'm just going to plow through. They're all named after him. They're all very important reactions. In 1892, he moved to the University of Berlin. You might remember that's the year that Hofmann died. Hofmann was the chair of chemistry. So he became the chair after Hofmann. And then most importantly, well, perhaps not most importantly, but as a vindication for all his work, he won the second Nobel Prize in chemistry in 1902. But one of the things he showed us is that we can identify the structures of molecules by synthesizing them and then comparing their properties, like melting points, with authentic samples. That's what takes us to our next part of our story with a chemist in Vienna by the name of Ernst Speth. So he's a phytochemist. This is a chemist who works on substances isolated from plants. And Speth was interested in a substance isolated from the peyote cactus. So peyote is a cactus from northern Mexico that indigenous peoples there had long been using for spiritual journeys, let's say. It contains a substance that's essentially a hallucinogen. That substance is called mescaline. So this mescaline is isolated from peyote, and in the early 1900s, Speth was interested in proving the structure of mescaline. It was controversial at the time. There were a number of chemists interested in this very thing. There were a number of proposals. And if you looked at the literature, everyone seemed to agree that it had a benzene ring with 3 methoxy groups, but there was a lot of argument over where the other 2 carbons and the nitrogen were. Did it look like this? Did it look like this? Did it look like this? Speth set out to prove the structure of mescaline, and he was going to do that by synthesizing it. So his hypothesis was that this was the structure of mescaline. And in order to prove it, he did organic synthesis. He started with a substance that was readily available at the time, and that's this one. And he did a series of organic reactions. So just to really quickly look at it, hydrogenation to replace that chlorine with a hydrogen, and then a condensation with nitromethane, which replaces this oxygen with a double bond C in the nitro group. Zinc reduction, which partly gets rid of some of these double bonds and gives you that. Sodium reduction, which gets rid of the rest, and we now have this structure. This structure that he proposed was identical to mescaline. So if you want to prove that this is identical to mescaline, you compare it to natural mescaline. And this is a scan from his publication in 1919. If you have your substance and mescaline and they both have the same melting point, it might be coincidence. But if you make a salt, and the paper was in German, but we can see the sulfate salt of natural mescaline and the sulfate salt of his synthetic mescaline had identical melting points. So that's even more evidence. And if that's not enough for you, well, he made 7 different kinds of salts, and you can see they all have identical melting points. So he essentially proved his synthetic mescaline was the correct structure, and it was identical to natural mescaline. So Speth made a bit of a career in phytochemistry in proving the structures of substances from plants. Mescaline is one of his biggest contributions to organic synthesis. Another contribution of Speth's, though, is in who one of his graduate students was. And that's the last story I'm going to tell you about today. And that is the story of Percy Julian. So this is Percy Julian here. So you can see he was born in 1899 in Montgomery, Alabama. He's an African-American man. His father was a railroad clerk. His mother was a school teacher. But in 1899, if you think back, his grandparents were slaves. So he is a descendant of African-American slaves. But his parents did all right, and then he got a good education. He attended Depaul University in Greencastle, Indiana. And against quite a bit of adversity, he did graduate with a bachelor's degree in chemistry. In fact, he was the valedictorian of his class. And that earned him a prestigious scholarship so that he could continue his studies, and he went to Harvard, where he got a master's degree. After a master's, the next thing you want to do is go and get a PhD. But to get a PhD, you have to do some teaching. And the administrators at Harvard didn't think that a white student population would respect a black teacher. And so they forbid him from teaching, which was essentially forbidding him from getting a PhD at Harvard. So he had to drop out of Harvard. He bounced around some other schools for a while. It was a long story. So this was 1923, but in 1931, he went across the ocean to Vienna, where this kind of racism didn't exist, or perhaps wasn't as bad at least. And he studied under Ernst Speth, phytochemistry. And what he did there was maybe not the most exciting stuff. He proved again some structures of molecules that were isolated from this particular Austrian flower. But the most important point is he got a PhD. He finally became a PhD chemist. He came back. We're not done there. It gets better. So he came back to the US, and he got a job as a lecturer at Depaul University, where he got his bachelor's degree. And in 1935, as a lecturer, he became interested in studying extracts of the calabar bean, Physostigma venenosum. One of the extracts of the calabar bean is this structure called physostigmine, which is an important drug even today in the treatment of glaucoma, Alzheimer's disease, certain low blood pressure, and it's also an antidote to certain poisonings. So this was an important material to be able to synthesize. And there was a race around the world. Several other very famous chemists at the time were trying to do this. One chemist from the UK, Robertson, who became a Nobel laureate for synthetic organic chemistry, had previously published a synthesis that he claimed was physostigmine, but the melting point was off, and it turned out he was wrong. Percy Julian was the first person to correctly synthesize physostigmine. It took 10 reactions. It began with something that was readily available to him at the time, this molecule called phenacetin. And you can see the atoms in red are still there in the structure of the product. So this was a monumental achievement in organic synthesis. While he was interested in the calabar bean Physostigma venenosum, he also not discovered, but he became familiar with another substance isolated from this calabar bean called Stigma Sterol. And that's the structure of it here, and that's going to become important in a second. So Percy Julian would have liked to become a professor. He had a PhD. That's the requirement you need to become a professor. But unfortunately, even at Depaul University, the school that gave him his bachelor's degree, that hired him as an instructor, would not give him a professorship because of his race. So he had to leave Depaul. He tried to find jobs at other universities. He went through a number of positions. Ultimately, never got a professorship because of his race. He had to so then look to the chemical industry. He almost got a job at DuPont, a chemical company. There was an offer on the table, and then he received a letter saying, "Oh, we hadn't realized you're a Negro. Sorry, no job at DuPont." Finally, he gets a job at a company called Glidden. You may have heard of this company. They make paint. Glidden was interested in isolating oil from soybeans. This oil was going to be used to make oil-based paint. And so they hired Percy Julian primarily because he spoke German, and they had just purchased an extraction facility from a German company, and they figured he could basically read the instructions. He helped them set up this factory. He helped them isolate protein and oil from soybeans. One of the things he discovered was that soy oil is a rich source of Stigma Sterol, this substance he became familiar with when he was studying the calabar bean. And he's a synthetic organic chemist. He likes to make things from substances that are readily available to him. So he said, well, if I have a bunch of Stigma Sterol, what can I make from it? And he made progesterone, estrogen, testosterone, cortisone. All of these are incredibly important to the pharmaceutical industry. You'll recognize their names, hopefully, as hormones. They're all steroids. Maybe you've heard that term steroid and you associate it with performance-enhancing drugs. The real definition of a steroid is that it's chemically related to the structure of cholesterol. So there's cholesterol, and the ster in cholesterol is what makes things a steroid. So all steroids have these four rings, 6665, 6665. And you see that all of these steroid structures. So Percy Julian helped Glidden, a paint company, break into the pharmaceutical industry. And this is an ad from a magazine, and it shows a couple of white guys probably doing stuff that really only Percy Julian knew how to do. And it's an ad for testosterone and progesterone made by the Glidden Paint Company. So Glidden made a lot of money off of the work that Percy Julian did. Now, he was a smart guy, so the postscript to this one is a happy one. And that is, in 1953, he left Glidden, started his own company called Julian Laboratories, and they made steroids, sold them, made lots of money. In 1961, he sold that company for $2.3 million. Now, this is 1961 dollars, so that is a fortune. And so in so doing, he became one of, not the first, but one of the first African-American self-made millionaires from organic synthesis. So that's about where I'm going to end this story, the story of the mosquito and the sea snail. So just to recap, if mosquitoes were not so abundant, causing malaria all over the place, never would have recognized that cinchona bark contained quinine and Hoffman wouldn't have asked Perkin to try to make it, who inadvertently discovered purple dye. If a certain species of sea snail weren't so rare, Perkin never would have thought to take that purple dye and sell it, which launched an industry of dyes and drugs that we saw now generates billions and billions of dollars in revenue and cures a lot of diseases. If it weren't for that industry, Hermann Emil Fischer wouldn't have discovered phenylhydrazine, which launched him down a career that proved things about stereochemistry and the structures of sugars. Ultimately, phenylhydrazine there leading to a Nobel Prize, establishing the idea that we could identify substances by their comparison, by synthesis, which led Basf to synthesize mescaline, but also to supervise in a PhD, Percy Julian, who launched a career in, and an industry in the synthesis of steroids that is still going on today. And so I hope, ladies and gentlemen, that I've convinced you that were it not for the abundance of mosquitoes or the rarity of a certain species of sea snail, the pharmaceutical industry as we know it today would not exist. Thanks.